Twitch viewers, we've decided to stream live for today's cosmology and meteorology segments. Twitch.tv/smAsho. Thanks to our YouTube subscribers. If you're viewing on YouTube, don't forget to press like and subscribe. Don't forget to check our playlists. There's lots of content besides the daily space weather, cosmology, and meteorology segments. Thanks again to our YouTube subscribers. We're also on BitChute. There is some exclusive content there. We are counting down to the solstice, by the way, which I consider cosmology. And by tomorrow, we'll be in the 30 sunniest days of the year, or the darkest days of the year if you're in the southern hemisphere, as we approach the solstice. Just a little over 2 weeks away, and we'll be streaming live for it at 11:32 and 9 seconds. That's 11:32 p.m. and 9 seconds Eastern Daylight Time. We are located in Lehigh Valley. Thanks to our new Twitter followers as well. Don't forget to check us out on Twitter. There's all kinds of exclusive stuff there. And don't forget to respond to our poll. We've recently put up a poll. Who is more important, Vladimir Putin or Joe Rogan? We've got another 4 days left in that poll. And thanks to everybody that responded to the poll on YouTube. I would also invite everybody to join our own websites. Check out smAsho Forum, our merch shops, smAsho Store, Smash Store, our social media links. You can find it all at smAshomash.com, our homepage. Thanks to Smash staff for all your hard work. Look for additional announcements about smAshomash.com coming soon. Thanks to everybody who's picked up merch. It's our cosmology segment. Here it comes. It's full of fascinating stories. First, about gamma ray bursts. So we've covered this story here about one of the closest gamma ray bursts. This one located at only 1 billion light years. So one of the closest ones, and guess what it shows, folks? It shows that self-Comptonization is an unlikely mechanism to explain what is causing gamma ray bursts. So this one's important as its X-ray and gamma ray emissions diminished at the same time. So the self-Comptoning of this is an unlikely thing. According to existing theories, it seemed very unlikely that even the most powerful explosions in the universe could accelerate electrons enough to directly produce the observed very high energy gamma rays. This is due to a, quote, burn-off limit, end quote, which is determined by the balance of acceleration and cooling of particles within an accelerator. Producing very high energy gamma rays requires electrons with energies well beyond the burn-off limit. Instead, current theories assume that in a gamma ray burst, fast electrons collide with synchrotron photons and thereby boost them to gamma ray energies in a process called synchrotron self-Compton. The observations of gamma ray burst 1908 190829A's afterglow now show that both components, X-ray and gamma ray, faded in sync. Also, the gamma ray spectrum clearly matched an extrapolation of the X-ray spectrum. Together, these results are a strong indication that X-rays and very high-energy gamma ray bursts in this afterglow were produced by the same mechanism. It is rather unexpected to observe such remarkably similar spectral and temporal characteristics in the X-ray and very high-energy gamma ray energy bands. If the emission in these two energy ranges had different origins, says co-author Dmitry Kongulan from Rikyo University in Tokyo, this poses a challenge for the synchrotron self-Compton origin of the very high energy gamma ray emission. So perhaps have a read on this one. It's in the phys.org Astronomy and Space section. Title, front row, reveals exceptional cosmic explosion. Here's another interesting one. Jets from massive protostars might be very different from lower mass systems. So as we've said many times on the channel, both low and high mass young stars or protostars propel jets outward, perpendicular to a disk of material closely orbiting the star. In stars with masses similar to the Sun, these jets are narrowed or focused relatively tightly near to the star in a process called collimation. Because most high-mass protostars are more distant, studying the regions close to them has been more difficult, so astronomers were unclear if this was the case with them. So yet another interesting article. We've had so many cosmology articles recently coming out that it's difficult to cover. One of the many reasons why we are striving to make the channel a full-time endeavor. So don't forget to tell your friends, foes, science noobs, and science pros about the channel so we can continue bringing you more and more varied content and more in-depth content about things like this. What is up with the jets from high-mass protostars? Are they even protostars, or are they just reflections of the environment in which they currently preside? Leave us a comment. Let us know what your theories are about why the jets seem to be so chaotic. I've got a theory. It has to do with precession. I won't go further into it. Just check out the article. Here's the astronomy picture of the day from apod.nasa.gov. It's the May 26th total lunar eclipse, along with some irregularly shaped oak trees. And this one was from Pinnacles National Park in Central California. The astronomy picture of the day. Today we're not going to pick any random numbers or anything like that. We're going to close out today's cosmology segment on this story. Which direction does the solar wind blow? Well, it's another interesting article. Our patrons already had access to this one. Which way does the solar wind blow? The answer is outward. The answer is radially from the surface of the sun. But in any case, this is a very interesting article. And it's talking about further advancing the computer simulations of the chaotic magnetic environment and so on associated with the way that coronal mass ejections propagate. We've seen many times on the channel, and I'm sure if you're a regular viewer of our channel, you've noticed that coronal mass ejections come out in a fairly chaotic fashion. They come out in bubbles, and they seem to do all kinds of weird things associated with their magnetic field force lines. And so modeling these is super important in terms of propagating, in terms of determining how these will propagate, their direction, their speed, when they'll contact the Earth, and so on. They're most important for people in space, but also for things like transpolar flights and so on. So check out this article. Which way does the solar wind blow? It's pretty important. And these images here that you're looking at, these are images from stereo A, stereo B, and from the SOHO coronagraphs. You can see this is a directly Earth-facing coronal mass ejection. It is a little bit oriented to the southwest, as you can see the brightest spot down here, and the magnetic field force lines indeed do agree there. And the modeling from stereo A and B would be great. Stereo B's magnetometer still does work, but the imaging suite of instruments on stereo B were destroyed in, I believe it was September of 2014, by a hardware anomaly. Not good times for stereo B. I'm not sure if we should maybe put another spacecraft out there, or what do you think? Let us know if you think we should replace stereo B. Anyway, check out the article. And thanks again to our patrons. That's today's cosmology segment. We'll bring you back Twitch for our meteorology segment.